So chapter 15.3 is all about atmospheric pressure and winds, kind of how the two are related. Chapter 15.3 goes over why we have winds, and that is both a question of climate as well as weather. From our class conversations, let's remember that climate is the average temperature and weather that a place experiences over a period of years. And the weather is just kind of day to day. What does the weather look like today versus yesterday versus tomorrow? So it might be kind of warm today and cold tomorrow. It might rain in a couple days. That's the weather. But a place's climate is that, in North America, generally, in the fall, it experiences this type of weather. In the spring, it experiences this other type of weather. So larger average kind of explanations would be the climate versus weather is just day to day. So this chapter kind of goes over why a lot of that happens and kind of feeds into that conversation about what is weather, what is climate, why do we have winds. So the first question that we need to understand is why air moves at all. So this first bullet point here kind of answers that. Wind is created by differences in air pressure. So if you have an area of high air pressure and an area of low air pressure, you're going to generate the movement of air. So the greater the difference in those two areas of air pressure, so in high and low air pressure, the stronger the wind is going to be. So if you have only a small difference between two areas, you're going to have a light wind. If you have a very high air pressure and a very low air pressure, then you're going to get a strong wind. So the reason that this happens, why we get areas of high and low pressure, is explained pretty easily through two examples, air at the equator versus air at the poles. So air at the equator gets a lot of sun. It warms up a lot, which is going to energize that air and make it less dense. If it is less dense, that makes it a low pressure zone because all that air is rising up. So as it rises up and goes higher up into the atmosphere, there's less air pushing down, which makes it a low air pressure zone. At the poles, on the other hand, where there is less sunlight and the temperature is colder, therefore the air molecules have less energy and become more dense. As they become more dense, they sink down towards the ground. If you've got a lot of air sinking down and therefore pushing down against the ground, that's a high pressure zone. Okay? So that high pressure zone versus low pressure zone is what's going to initially cause air to move. So at its simplest, the reason that we have air moving is because at the equator, warm air is going up, and at the poles, cold air is going down. So these are two really good words to memorize, or not memorize, but to learn here and understand. Low pressure zone is an area where warm air is rising up. It's going up in the air away from us, so air is not coming down on us, so it's a low pressure zone. High pressure, meaning the force over an area, how much air is pushing down on you. So that happens where cold air is sinking. So surface winds are where they blow from the poles to the equator, right? They come down from the poles where that cold air is sinking, and then at the equator, they're starting to warm up, so they rise up and leaving space for that cold, dense air to enter from the poles. So that's explained in this picture here, right? So in a low pressure zone, you've got warm air, right? So we're going to write that in here, warm air. And as that air warms up, it starts to become less dense, and it is going to rise up and essentially float on top of colder air around it. So as it starts to float and move up into the atmosphere, it moves in this direction. We're going to ignore for a moment the clouds versus the sun. So let's say this is over here at the pole, and this is at the equator, okay? So that air eventually travels up to the pole where it cools down. So it is cold up here. As it gets cold, it gets more dense, and therefore that air is going to sink back towards the ground. As it sinks back towards the ground, that is what is known as a high pressure zone. It gets pushed this way, and it gets pushed this way because of the air that continues to come down from above, right? It's like people kind of pushing you from behind and pushing you out of the way. there's only two directions you can go since the ground is here. You either go that way towards the equator on one side of the Earth, or you go down this way towards the equator on another angle, right? So that this air eventually warms up and goes back up here. It then cools down and goes down. And see, so we call this a convection current. Convection current, right? Where that warm air goes up, cools down, sinks back down, warms up, cools down, and sinks, right? So the reason that they've got these clouds here is as this warm air goes up, what happens to its temperature? Well, we know that in the stratosphere it gets colder. So as it gets colder, it's going to lose energy. So the water in that air, the water molecules that are in that air, are going to condense. And we've already learned what that word means back in the first quarter. But for it to condense, that means that water goes from a gaseous state to a liquid state. As that happens, we see clouds form. So it's not that water all of a sudden appeared, it's that the water that was once water vapor or water gas condensed into liquid water, and we see clouds form. Over here, as it's getting colder, right, it probably rained at some point, and the air is pretty dry and cold, and as it gets colder, it sinks down to the Earth. So let's say rain right here, right? Now that's getting a little bit complicated in talking about condensation versus the air and the rain, which gets more into precipitation and weather than we're looking to do right now. This, at first, we're just explaining why the air is moving. Then later we can look on how that affects your day-to-day weather and rain and that kind of thing. So pressure belts, there's not one huge circular pattern, but many smaller patterns called convection cells or convection currents. So that's what we drew just up above, right up here. So how it works, warm air around the equator or any low pressure zone rises because it is less dense. As it rises, it cools and moves towards the poles. Continues cooling, condenses, and falls back towards Earth. This wind then travels along the Earth and warms up, restarting the cycle. And so right here we mentioned that this happens in many smaller patterns, not just one huge circular pattern. So that's why up here we talked about, the equator and the poles are the two main places that this happens, but that's the simplest way of thinking about it. Every 30 degrees of latitude, you're getting one of those cells. So there's essentially like 3 cells in the northern hemisphere and 3 in the southern hemisphere where this is happening. If we flip down here, this is a great picture because it shows all of those cells happening. The equator is a little bit warmer than this subtropical high, which is a little bit warmer than right here at 60 degrees, which is a little bit warmer than right here, right? So here's one cell, here's a second cell, and here's a third cell. And so it's not just one giant one that goes all the way like this, right? It actually is 3 smaller ones because of these small differences in temperature versus here, 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 and right here. Because of those 4 differences, you get 3 cells in each one of those. Okay? Those are known as Hadley cells, or those are known as convection cells or convection currents, right? Those are all kind of the same words to describe the same thing. I love this image here. It goes over a lot of those vocabulary words like Hadley cell, horse latitudes, westerlies, polar fronts, polar easterlies. So it's a lot of those winds that we see right here. You actually get a visual of them down below. As you know from me and from science class, we don't do a ton of definitions. So we're not actually in this video going to review each one of these because the definitions are all right here. You can copy them down. They're pretty simple. So if you want to right now, flip to the second page of notes and give this video a pause, and you can fill in all of these little definitions. Most importantly is as you look at this definition, for instance, or look at the trade wind or the horse latitude or something like that, go down here and find where the trade wind is, or right here, right, or where the horse latitude is. It's, why it's called that. There's history to it that's explained in 15.3 about, they had to dump a bunch of horses off of a boat because they ran out of winds and that kind of stuff, so they needed to make the boat lighter, right? They kind of got stuck. What's interesting is that all of these winds are kind of going in different directions. So as this air heats up and moves back down towards the equator, it's going to essentially, the wind is going to move west as that happens. And as this Hadley cell does the same thing, that wind is also going to be shifting west. Now, off of this pattern right here, off of the convection cell between 30 degrees and 60 degrees, that wind is going to move east. And interestingly, they're called the westerlies because they're coming from the west, moving east, right? So this image here not only explains what a Hadley cell or a convection cell is, it explains individual winds that we've got and the names of those, but it also shows you how the Coriolis effect, something we haven't just yet talked about, Coriolis effect, determines the direction of the winds. So that's what we're going to jump up to right now. So the Coriolis effect, just the definition, is that the rotation or the spinning of the Earth causes the wind to curve. Now, we can all understand that definition, and essentially like the string of words and what they mean, but how that works and how that happens is a little bit more complicated. So if we're thinking about this circle here, this big sphere, right? This is where we live. This is planet Earth. Let's pretend for a minute I'm making this number up, but let's say, and I'm picking this number because it's easy for math, let's say that that width, or that circumference rather, at the Earth's equator is 2,400 meters. Okay, you'll see in a minute why I picked that. And let's say up here, it's only 24 meters. Okay, 1,000 times difference. So if we are calculating speed, this is something that you learn a lot more in 8th grade. Speed is distance over time, meaning how far you travel in a period of time. So if we're looking at the equator, you travel 20, and you're standing right here. You travel 2,400 meters in 24 hours, meaning that if you were here and you then travel all the way around, well now wait a second, do we travel all the way around? No, the Earth is rotating all the way around, right? So if the Earth rotates all the way around in a day, that takes how much time? Sorry, rather, we know how much time it takes, 24 hours. How fast is the Earth spinning if you are standing right here? Well, 2,400 divided by 24 is going to equal 100 meters per hour, right? So if instead you're standing on the North Pole and you're standing right here and you're just standing there as the Earth rotates on its axis, how long is that going to take to happen? Well, we know that the Earth rotates on its axis every 24 hours. So whether you're standing right here or right here, it's going to take you 24 hours for the Earth to spin on its axis. So if you only have 24 meters to go up there, that means that the Earth up at the top, at the North Pole, is only going to move at 1 meter per hour. So what I showed you here is that essentially, if you were standing at the equator, or if you were standing at the North Pole, you were traveling at two different speeds. Granted, you're still on Earth, and Earth is moving through space at the same speed, but Earth rotates based on whether you were on the equator, or at the North Pole, or the South Pole, at very, very different speeds, because of the circumference of the Earth, depending on where you are standing. So if you're up at the North Pole, you're actually moving very slowly. But if you're at the equator, you're moving very quickly. So the difference in speeds here means that as wind comes off of the equator, it's going to move a lot faster than if it is moving off of the poles, which is essentially what this picture here is showing you. Faster at the equator and slower at the poles. So, as Earth rotates or spins to the right, any air that is coming off of the equator is going to carry with it the speed of the equator, the momentum of that motion. So if I were standing right here and I threw a baseball 5 miles an hour this way, I'm also moving, based on our calculations, 100 meters an hour this way. So that ball, its path, is going to move in this direction, right? Because not only does it have the force of my throw in this direction, but it also has the force of my throw in that direction, because I am standing at the equator and moving very quickly in that direction. So the ball is going to actually travel something like this, which is why our winds, when they're moving in that direction, moving north or south, spin this way. However, if you are standing at the pole, where you're moving really, really slowly compared to down here, right? If I'm moving slow up here compared to down here, if I throw the same ball at the same speed, at 5 miles an hour this way, or 5 meters an hour this way, and the Earth down here is wicked fast compared to where I am, it's moving way faster this way, the ball is going to actually go behind me. It's like if you are on a motorboat and you throw a ball to a friend on another motorboat. That ball is going to go behind you. And that's because the air that you throw the ball into, the air on the lake or the ocean or whatever, is moving a lot slower than you are on the boat. So it's going to apparently move behind you, which is what happens when air comes off of a pole and moves, so here's the other pole, and moves south. Okay? So if we flip down once again to the drawing that I love, as you're standing at the pole, the air moves south and it moves west. Moves south and west. And here, technically, it's moving, I guess it's not necessarily further south, but closer to the equator, and the wind is going to go south, right? And then as you're coming from this one, if wind comes off, it's going to move this way. And then if wind's coming from here, going further south, it's going to go towards the west. If wind's coming off of here, it's going to go towards the west. Wind comes off of here, it goes towards the east, towards the west, right? And so all of the air is going to do that. As air moves closer to the equator, it goes west. So closer to equator, it goes west. If it goes closer or travels to the poles, right, closer to the poles, it's going to go east. Now, again, why does the wind that's coming from right here go this way, meaning go towards the poles? Well, that's because of this Hadley cell. Right here it's really hot, so it rises up in this direction, leaving space for wind to fill in behind it. So it goes like, right? And that's happening right here. Big Hadley cell. Big Hadley cell. And it happens all over the Earth. So wind from 30 degrees here moves west as it travels back towards the equator. Now I know that was a ton of information that we just talked about. Some of this is really confusing, right? We start pretty simple up here. We say, okay, where it's warm, air is going to rise up because it's less dense. That's something that intuitively makes sense because we've been studying the effect of temperature on energy and on density, right? And then when it's cold, that air is going to condense, it's going to sink down, right? That makes a lot of sense. So then we tie those together into convection cells, right? And you're going to realize that we've got not just one huge one that travels all over the Earth, but we've got convection cells at every 30 degrees of latitude. So essentially we just have many convection cells all over the place due to differences in temperature, right? Okay, so we're still there with it. But then it gets even weirder when we add in this whole Coriolis effect, right? And then the direction of the wind. So the way that I always like to think about this is by coming up with examples, right? If I'm standing at the equator and I throw a ball, which direction is it going to go? If I'm standing at the poles and I throw a ball, which way is it going to go? Another way that you can think about this is if you are on a motorboat, right? And you throw a ball, and you're trying to throw a ball to a friend that's on a dock, right? And as you throw the ball to the friend that's on the dock, if you're on the motorboat, that ball is going to travel with some of your momentum and land in front of or ahead of the person that's standing on the dock. If the person on the dock is trying to throw you, who's on the boat, a ball, that ball is going to end up behind you, right? So you're going to have to adjust the path that you throw it. We know this intuitively from sports, and we'll do some examples of it in class. But a key thing to remember here is that if the air is moving, so if air is moving, closer to the equator, it's going to go west. If it is moving closer to the poles or towards the poles, it's going to move east. We'll go over all of this in class, but this is good just to have this video here with some of this information so that you can kind of watch it again and again to make sure you get it. Also, don't forget, here are the notes with the type of winds if you need to fill that information in. There's a lot of great videos out there about the Coriolis Effect. If you want some good visualizations, I'll add them into the 6th grade playlist on YouTube.